In this lab, we're going to see how an application can be enhanced using the Intel Mobile Platform SDK. Applications usually don't have any awareness of connectivity, such as is there a network connection or not, how much bandwidth is available, and it doesn't really know what the power status is. So if bandwidth is low, connections drop, or the battery level starts dropping, performance in the application will suffer. Users will most likely complain or just be dissatisfied, and that doesn't need to be this way. We're going to start by talking about the existing CRM application. We're going to start by looking at mobility in the operating system, seeing some of the settings that users can select, and then we'll talk about some incorrect assumptions being made in the CRM application, things that are just fine to make as long as you're plugged in and you have a steady connection, but of course in reality you can't ever assume that that's going to be the case. So to begin with, just as a point of example, if you've ever used Outlook in Exchange mode, think about how that works in an offline, online mode. You don't need to specify anything. It automatically manages that for you. So we'd like to try to recreate that sort of thing in other applications where it simply knows it's online or it's offline. We don't want to be giving lots of error messages to the user. We don't want to be draining the battery too much when it's already low. We don't want to be overutilizing the network connection, degrading other applications, and we certainly want to make sure we don't lose any data if the system goes into standby mode or it shuts down. So let's look at the power options properties that users can select in their system. This can have an impact on how every application works, as this affects when the system is going to go into standby mode or turn off its hard disks. There are some built-in power schemes: home and office desk, portable laptop, presentation, always on, minimal power management, and max battery. And then users can also just set their own amount of time to turn off the hard disks or go into system standby, depending on whether it's plugged in or running on batteries. You define, based on power level, alarms. If the system hits, in this case, 10%, it's going to make a text notification. These are the default settings. No change has been made here. If it gets down to 6%, it's going to say that. Again, it's going to say your battery level is low. It's critically low, and in fact, the system is going to go to standby. If your application isn't monitoring for this, it's going to come as a surprise as all of a sudden you get a standby message, assuming you're even subscribed to that, and the system will just go down then, and there's probably not going to be enough time for you to intelligently respond to that. The power meter allows you to see the current battery information, what level it's at. And if it's running on battery power, it'll tell you how much time is left in that as well. Currently it's plugged in. So we're going to start up the middleware server. The CRM application requires the middleware server to be running. And once it's running, we can open up the solution. We're on day 4 today. Go to the hands-on lab. So this is the existing CRM application. It's built and ready to run, or at least it's ready to build and run. But at this stage, it has no mobility awareness. So we're going to see what probably resembles a lot of corporate applications that are written for the desktop and don't have any awareness of battery or network, system standby, various things that can happen on a system. Even on a non-mobilized system, you can enter standby mode. So these are all things that an application needs to be aware of. And of course, as a corporate application, there's a good chance it's going to end up being run on laptops, and so it makes these factors even more important. So if the application started, we can test basic functionality. We're just going to do a simple search to begin with. We've got our users. So we know everything is working properly. And this is the simplest case, and this is what most people assume. You've got a network connection. Maybe some developers might put a try-catch there because, of course, it might not connect, and then you'd present an error message to the user. But if a user is going to be offline for a period of time, it's going to be pretty annoying getting an error message each time. It's going to make more sense to maybe cache updates, or to, if nothing else, at least silently deal with the error somehow behind the scenes without the user being explicitly aware of each message. So we're going to want to disconnect the network connection. Essentially, you go to your network connections, you can right-click and disable a network connection. And that's a good way to fake it. In this case, we're running the middleware on the same machine, so network connection or not isn't going to make much of a difference. So we're just going to close the middleware window, and that will be as though the user was on a remote machine trying to connect, and of course it won't. Let's start up again. This time there's nothing running in the background. It's as though it's off the network. And what's going to happen? With absolutely no mobility awareness in the application, it's going to try, and it's simply unable to connect. It's probably going to continue to try until it times out at some point. And as you can see, unable to connect to the remote server. If this was not running in debug mode, the user would have a crash right now. They'd have the send, don't send option to report an error to Microsoft. Very, very bad user experience. Even if it did pop up a dialog box, it's still probably not going to please most users. All it tells you is that you're offline, but what does that mean to the user? They're completely unable to work. So ideally, we would want to handle this proactively, detecting that we're online or offline. And if we're offline, not just present errors to the user. If you've disconnected a network connection, if you're trying to follow along with this at all, you'd want to reconnect your connection at this point. And in the next exercise, we're going to want to try to start adding some of those features so that we can better respond to these connectivity changes. So we've taken a look at basic Windows level mobility management with a control panel applet. We've taken a look at what happens to an application when it's not mobility aware. So now it's time to add support for the Intel Mobile SDK so that we can respond to bandwidth and connectivity and power issues. One way would just be, of course, to attempt to connect, and then if it fails, set an offline flag. But by using an event-based approach, such as the Intel Mobile SDK, we don't need the user to initiate anything. We can be made aware of changes to the system, and that's going to provide for a much better experience. So in order to use the Intel Mobile classes, we're going to want to add a reference to the project. We're going to need to point to the various DLLs that are then accessed using the pinvoke mechanism. These are all managed libraries already written that already wrap the functionality to make it really easy. Notice the CLR designation in these. All of these have been written to wrap the functions so that we can access all of the features. And we don't need to do any pinvoke. We don't need any DLL import. We don't need to declare any extern methods. All of this is going to be done for us. They've all been read in, added to the project. So now they can just be used like any other .NET class. Let's go to the main form, view code. And we need to add some new using statements. These namespaces allow applications to take advantage of the three capabilities present in the SDK: power, connectivity, and bandwidth. Capabilities are a higher level of abstraction than just working with the individual devices. They let you determine things like the network speed without needing to actually go through enumerating all of the devices and querying various properties. The capabilities are accessed using the context class, and then you can get specific instances of different devices on the machine. So now that we've declared the using statements, we can use them in our application. So let's make some class level members. So the Mobile SDK supports three capability types, and this may well be expanded in the future. And using these, you can obtain enumerable information using the getInstances method of the context class object, or you can use the getInstance method if you know the name of the capability as a parameter. Let's actually create an instance, and this will be in the constructor. Create a new block. We've already declared my connectivity as a connectivity instance. So from the context, we're going to get a named instance. We could have gotten instances. And that would have given us the entire collection through which to iterate, but we're just grabbing the specific instance named connectivity. And because getInstance is a generic method returning instance objects, we need to then cast it as, in this case, a connectivity instance because we know what it is. Instance objects have shared properties, so it would still be useful if you were enumerating. You could find the name of it and find various information, but you can't get to the specific information that you're most likely interested in. Now, in order to take advantage of the connectivity class, you're going to need to write code to respond to its events and to look at its properties. There's a property called connected, and that's used to determine if you're connected or not. Using the connected flag, you could just check every time the application is about to save remotely, but that might be a little bit more work involved than responding to the event of changing your connected status. Instead of just checking every time we're going to save, don't even bother trying to save unless you know that there is a connection already. In order to do that, we're going to need to add a new class. When you're responding to events, instead of using delegates as you would in typical .NET programming, the mobile SDK uses the observer model. And the intel.mobile.context.observer class defines a notify event. And so you can subclass that and override the notify method in order to handle an event occurring. We're going to actually bridge a delegate and the observer together. We're going to make a new class called delegate observer. So let's add a new class, and we'll call it delegate observer. We'll need to add some using statements. And we have a new method that we can paste in. And so we're still in the same namespace, but now we've declared a delegate called observer notify delegate. And that will take an event as a parameter, returns a void. And then we've declared the delegate observer, which is an observer object, and because it descends from observer, it needs to implement or override the notify event. When you create an instance of the delegate observer, you pass in an observer notify delegate, so we'll have to define a method elsewhere that takes an event and returns void. When notify is called, it invokes the myNotifyDelegate method, passing whichever event was passed in originally to the observer. So now instead of needing to override the notify method in our code, we can now create any method that we want to as long as it follows the observer notify delegate pattern. And then we can register multiple events, so we don't have to worry about the problem that we can only descend from one class. So in order to subscribe to the connect event, two things need to be done. First of all, we need to change from STA to MTA. STA is just not compatible with the Intel Mobile Platform SDK. If we don't do this, the events aren't going to fire, but we're not going to get any errors. It will compile, it'll run, but we're not going to get any events. So that one letter just changes from STA to MTA thread on the main thread, which is where we need to worry. This is where the UI is going to be. So we're now compatible. And now if we switch back to the main form, we can create the observers and subscribe to the events of interest. So after the connectivity declaration, we'll create an instance of the connectivity change observer. And that's a new delegate observer, which will be pointing to the method connectivity event handler. And then on myConnectivity, we have a number of methods. We also have a number of properties. We've got connected and disconnected, IP address changed, is connected, route table changed, and status changed. We can subscribe to connected and disconnected. We can read them as properties or subscribe to them as event when they change. If we use status changed instead, that will tell us when it connects or when it disconnects, so we don't have to subscribe to do different things. We can check to see if a property is available. We can remove an observer. We can add an observer. So we're going to add the connectivity change observer that we just created. And then we'll initialize it by invoking the connectivity event handler method, being called directly as a method. That way, we can initialize information when the application starts up. We'll need to call remove observer when the form is closed. Failing to do that, we'll cause resources to be left and will cause problems if we try to run the application again. So let's scroll back up to the end of the constructor, and we'll create the connectivity event handler that we referenced here. Private void event E. This is exactly what we declared as a delegate observer, so it will accept an event as an argument and it returns nothing. This method is what's responsible for actually dealing with the fact that we've just gone online or offline. When you go online or offline, you need to allow the user to still be productive. So we don't want to just shut down the application. We don't want to just say, whoa, we're offline, you can't do anything. So changes will still be collected in the background in the data set. They just won't be sent to the database. So when we're invoked, that means we've just gone online or offline. Because the Intel Mobile SDK events happen on background threads, they're not able to manipulate the user interface. So we need to have the user interface, we need to invoke this method on the user interface thread, and that's what the invoke required checks for, and then invoke actually does. It adds a call to the message pump for the form so that it occurs on the proper thread. And then after putting that onto the message pump, it returns. So the event handler then invokes itself that way. This time it's able to check if it's connected or not. It makes a check to see if we're truly online or not. In an enterprise environment, you'd probably want to put the address of the server that's running the middleware, and then if it was able to reach it, because we may be online, but we may not be able to hit the server that we're attempting to reach. Assuming both is true, then we can say that we are online. On the other hand, we might be connected to a network, but not able to reach our host, in which case, let's just say that we're online and no host. Otherwise, we're offline. Finally, we'll tell the data access tier that we're online. And this is how we'll keep that in sync. Now let's go to the data access class. And in the constructor, we're going to remove these lines. And we're going to create a new method. And we'll use this to initialize the data access tier. We'll clear any existing customers. We'll retrieve the new customers. We'll load from the cache in order to read any local information we already have in our local database, which may include changes. This step will also then merge that data, so any data that we retrieved from the database and any data we had locally will be merged together. And then we'll update our local cache so that if we come online next time, if we're launched next time and we're not online, we'll still have data to use. But we do need to make sure that retrieve all customers is respecting whether or not we're online or offline. If you look down and retrieve all customers, we clear the table, we retrieve all context. But what happens if there's an error here? There's nothing checked there. First of all, let's change this to reflect the fact that we might be loading from the server or from local data. Next, we'll retrieve from the remote data if we're online. Otherwise, we'll load from cache. Now it's possible that we will attempt to connect online, and even though we have our online flag set, we're not actually online. So in that case, we're going to need to take an extra step that when we think we're online, we still want to wrap this in a try-catch clause. So we're ready to go to main form. And after initializing the capability display, let's initialize the data access tier as well. We'll want to make sure that we relaunch the middleware first. Waiting for connection. And we're ready to start debugging. And as it indicates, we are online right now. These other statuses will be used later on in the lab, and that's why they've got hard-coded place values right now, but the online did set properly. Now let's disconnect the network cable. As you can see, the system tray indicates it's offline, and so does the application. When we plug in the network cable again, it responds appropriately, and the application knows it's again online. So now we've added the ability to check for online and offline status in the application. But it would be good to also monitor the bandwidth that's available. The Intel Mobile Platform SDK lets you detect the amount of bandwidth available on the system. It also lets you place limits on how much bandwidth is available for upstream or downstream usage. This makes it really easy to allow different applications to use a proportional amount of the bandwidth instead of adversely affecting each other with all of the applications trying to use all of the bandwidth. Just as with bandwidth, connectivity is available through the capabilities object. The bandwidth instance class has information about the current bandwidth divided into transmit and receive. So after the connectivity instance, we'll declare a bandwidth instance object. And we can use that then to query for bandwidth information. And we'll declare a second observer. And the bandwidth change observer will be used every time there's a change in the bandwidth that we want to monitor. Let's go down to the end of the constructor. After the connectivity block, we'll add the bandwidth block. And just as before, we had to use the getInstance object with a name, and then we casted it to the instance we were looking for. This time we're looking for the bandwidth instance, which will return as a generic instance object, and then we'll cast it as bandwidth instance. You can now access the bandwidth-related properties anywhere in the application. You could use that to display the actual or the in-use bandwidth. But instead of just polling for the levels, you can also respond to changes in bandwidth using the same event mechanism used for the connectivity capability. So just as before, we'll declare the delegate observer and add it as an observer. And the bandwidth event handler isn't yet declared, but we'll get to that in a moment. And just as when we added observer with a connectivity change observer, we'll add the bandwidth change observer as well. After the connectivity event handler, we will now add the bandwidth event handler. This has a bit more code. And if we scroll up, once again, we want to make sure that we're on the right thread. Recall that the mobile SDK is on its own thread, and we need to make sure that we're running on the UI thread because we're going to be updating the controls. So we've been invoked because the bandwidth property changed. So we're going to check first to see if we're even online, just in case in that moment between when the event fired and now we've gone offline. If we are online, then we're going to check the limits, see if our receive is limited at all. If so, how much is it limited to? And then we'll set the RX limit number to that. Otherwise, we'll set that to the theoretical system rate for receive value. And then we'll do the same thing for transmit. And then we'll set the status, the net speed tool strip information for the up and the down. Otherwise, we'll set a dash there if we're not actually online. Once again, we'll need to remove our observers at the end when the application is closed so that we don't leave any resources hanging. And finally, we'll need to initialize this when the application starts up. Just as we call the connectivity event handler, we need to call the bandwidth handler. And just as with the connectivity event handler, we pass a null event. The event handlers aren't actually looking at the event object itself because it's then querying for the properties, so it's irrelevant if we're passing data there or not. We're now ready to debug the application. And the application has started. And we can now see that we're online and that we're on a 100 megabit per second connection, both up and down. So the application could make a decision now that because it's online and because it has a very high bandwidth connection, it would make sense to let all of the updates go through to make any changes that need to be sent over the network without worrying about throttling it all, because there's plenty of bandwidth. As stated before, allowable bandwidth can be modified, not just retrieved. We might want to put a limit on the bandwidth that we are consuming so as not to slow down the system, or we might want to make it easy for the user to throttle an application to better prioritize across the system. So we'll bring up the main form in design mode this time. And you may have noticed the Manage Bandwidth Limits button over here. It's not currently wired up to anything. So we'll double click that to create a click event handler. And here we'll add code to manage the bandwidth limits for this application specifically. The bandwidth regulator form is already set up To allow users to make changes to allowed bandwidth for this application, that is how much transmit and receive bandwidth is available, the bandwidth form sets the maximum receive and transmit rate based on the theoretical system rate Rx and Tx properties. Then the current allowed bandwidth rate is based on the limit Rx and Tx properties. So the system's theoretical system rate may be 100 as it is right now, but we may set the limit to be only 20 or 10 or something smaller than that. The Intel Mobile SDK does ship with a bandwidth management module, and this is installed automatically, and this also lets you control the bandwidth for applications. So for each system that's running, each application that's running, you can set what it's currently using, you can view, you can also set the limits, whether as a percentage or as an absolute number, and you can set it independently for download and upload. We're going to be setting this via the API directly within the application. So once we've initialized the values, we'll need to show the dialog. We use the show dialog method of the form so that it's modal, and it'll wait until the user clicks the OK or cancel button. If they did click OK, then we're going to take the allowed Rx and the allowed Tx from the form and set it back into the bandwidth, limit Rx and limit Tx values. Indicate that there are limits now by setting the limited Rx and the limited Tx properties to true, and then force an update of the bandwidth display. And let's see that in action. And the application is launched. We're online. We've got a 100 megabit per second connection. Manage the bandwidth limits. We'll do 256 for the limits. And we did not directly update the status property after changing the bandwidth form. Remember that we invoked the event handler, so it then queried the bandwidth object. And so this is how we can determine that the bandwidth has indeed been set to the 256 number. Now we'll do a search on Anderson. And instead of the instant response that we've been getting previously, we're now having to wait for several seconds as the data is retrieved. Once again, evidence that a limit is in effect. So in the final exercise for day 4, we're going to react to power state changes. Bandwidth, connectivity, and power are the 3 supported capabilities in the mobile platform SDK. So just as with bandwidth and connectivity, we'll declare power in the same way. And we'll need a third observer defined here. Power change observer. This will be invoked when we have a power change. Then after bandwidth, we'll add a power section. Now, of course, we're going to want to subscribe to the event to simplify things. We don't want to be querying for the event every time, for the power amount every time. So the first thing is from the myPower object, the source property, we want to know when it's changed, and add an observer to alert us when that happens. So we want to know if the power source changes from battery to AC. Similarly, if the capacity changes, if we're on battery power, if we change the capacity because we're draining the battery, we also want to know that. And then finally, we'll want to initialize the capability. And power event handler doesn't yet exist, so we'll scroll down after connectivity, after bandwidth, and we'll create the power event handler method. Once again, in a repeat of the pattern, we want to make sure that we're invoking in the proper thread. And we're going to declare a string variable to hold the plain text version of what source we're using. If the source equals internal, that's the battery, otherwise it's AC. The source enum also has external, so we could check explicitly for internal or external. All we do is we set the status label then to the word battery or AC, and then based on the percent remaining of the battery, we'll set the percentage. As before, we want to make sure that we clean up properly so we don't leave any resources hanging. So we're going to check the source property if it's changed. We want to remove an observer and also remove our observer on the capacity. And we're ready to run the application. And we're online. We have 100 megabit per second of bandwidth. So we'll start out by using AC. And now if I disconnect the power, you can see the battery in the tray and the application shows battery. Plug it back in. Switches back to AC. You can see we've already used up some of the battery just in that brief amount of time. So we've now implemented all 4 of these. So we can exit the application. And the final thing that we want to do is use the threshold object. We've used the delegate observer now for property changes, but we can also set a threshold if we don't want to be notified every single time the value changes. In order to do that, let's go to the top where we declared the instances. The uint gauge threshold will respond for numeric values and allow you to set a range of information of interest. As with the other observers, the low power change observer will be a delegate observer object. And now we'll need to actually create that object. And we'll do that at the end of the power block. Battery threshold needs a delegate observer. This is what will be invoked when a threshold is hit. Then we create the actual threshold itself. We want it to fire once a second to check to see what the value is. Notify if the value is high or if it's low. Low value being 95, the high value 98. As soon as it gets as high as 98, it will alert us, or if it gets as low as 95, it will alert us. It's kind of like a thermostat in that respect. We set which property we're actually interested in. Percent remaining. Add an observer that we just declared and start. Just like with a thread, you want to start it, and then it will, based on its granularity period, its interval, it will query for the property amount. So let's clean up our resources again. From the threshold, remove the observer, low power change observer. And then, of course, we want to implement the actual event handler. So after the power event handler, this will be its entirely separate handler. So we'll insert the code for the low power event handler, which checks to see if we need to invoke on the correct thread. And then it determines if it happened on the low threshold, in which case the battery is too low. Let's set our color to red. Otherwise, if it's on high, that means we're back to good. We're going to set the background for that status strip to the control color, what's thought of as the neutral gray. We'll go to debug, and we'll start debugging. This one might be a little bit harder to demonstrate since it's based on the battery hitting a certain level, so it might take some time to hit that point. So we'll artificially speed it up so that we can hit that point faster. So we're on AC with 100% battery, and we'll switch to battery at 99%. And we've let it run down to 93%, so it's below the minimum threshold. You can see that the background color in that status region has now turned to red, as expected. If we were to plug it back in now, we could let it charge back up to the 98% level, and it would change back to that known color .control, that neutral color that would match the background of the other status controls. So hopefully you can see that there's a lot of power in the Intel Mobile SDK for enabling battery, power, and network awareness, in addition to many discovery capabilities. Download the trial and give it a try in your own applications.